Welcome to the deep dive. Today, we're really getting into something pretty advanced in AI. We're looking at how these models can do complex reasoning, multiple steps, not just churning through text.
That's right. We're diving into a framework called reasoning by superposition. It's a fascinating way that transformer models might be achieving what some are calling a chain of continuous thought.
Continuous thought. Okay, so not like the usual step-by-step thing.
Exactly. And it's especially interesting for problems like figuring out connections in complex networks like graphs. The mission today is really to understand the innovation here.
Right. So the big question for you listening is, how do these transformers manage this multi-step thinking so efficiently? What's the new idea, the innovative spark that makes this so much better than, say, older methods?
Yeah, what are the key innovative points?
We want to give you a kind of shortcut to grasp how modern AI might be thinking when it tackles these tricky problems. And honestly, some of the insights are pretty surprising.
Definitely. So maybe let's start with the problem they tackled. It's called graph reachability.
Okay.
Imagine you have a network, right? Nodes connected by arrows, but maybe only one-way arrows. You've got a starting point, the root, and then you have two other nodes, potential destinations. The task is, which one can you actually reach by following the arrows from the start?
Seems simple enough on the surface, but I guess it gets complicated fast.
Oh, absolutely. It's fundamental, though. It pops up everywhere. Knowledge graphs, theoretical computer science problems, logistics, you name it. It's a core reasoning challenge.
And you mentioned before, AI usually tackled this with chain of thought, CoT.
Right, traditional CoT. With that, the language model, well, it writes out steps, discrete steps in text, like first I check this, then I deduce that.
Like showing your work in math class.
Exactly like that. It spells everything out sequentially, which is helpful, but it can be really slow, computationally heavy, especially if you need lots and lots of steps. Each thought is separate.
Okay, so that's the old way. What makes this chain of continuous thought different? What's the breakthrough idea?
This is where it gets really interesting, I think. The core innovation is moving away from discrete steps entirely. Instead, they talk about continuous thought and superposition.
Superposition, like in quantum physics.
Sort of. It's an analogy, but a useful one. Instead of generating separate text steps, the transformer maintains its thought as an internal state, a vector that represents multiple possibilities at the same time. It's a superposition state.
Whoa. Okay, I'll back that a bit.
Yeah.
Multiple possibilities at once.
Yeah.
How does that work for the graph problem?
Well, think about the old way. CoT might try one path, hit a dead end, backtrack, try another. Very one-track mind.
Sequential?
Right. With superposition, the model's internal state, this single evolving vector, can simultaneously represent a blend, a weighted combination of all the nodes it thinks might be reachable at that point.
So it's not just thinking about one path. It's implicitly holding information about many potential paths simultaneously.
Exactly. It's like doing a parallel search inside its own representation, kind of like a breadth first search or BFS, where you explore level by level outwards from the start. But it's not explicitly running BFS steps. It's happening implicitly within this continuous vector state.
This sounds way more efficient.
Hugely more efficient. This is the key theoretical leap. The paper actually mathematically proves, that a simple two-layer transformer using this continuous thought for, say, D steps, where D is the graph diameter, the longest, shortest path, can solve graph reachability. Now compare that to a standard transformer using discrete CoT. Even with the same depth, it might need something like ON2 steps to decode the answer, where N is the number of nodes.
N squared. That's a massive difference. That's the innovative result you mentioned.
It's a colossal difference. We're talking potentially exponential gains in efficiency for this kind of reasoning.
And the most mind-bending part you said earlier is that this isn't explicitly programmed. It just happens.
That's what's so profound, academically speaking. This sophisticated superpositional search capability emerges during training. The model isn't given instructions like, explore these paths in parallel. It learns this efficient internal strategy on its own, just from learning to predict the final answer.
An emergent property. It's pretty well. Okay, so how? How did they build a transformer that can do this? What are the nuts and bolts?
Right, let's get into the how. One of the really clever design choices is about the token embeddings. You know, how each word or symbol is represented as a vector.
Yeah, usually just a big list of numbers.
Well, here, they didn't just use a big blob of numbers. They engineered the embedding vector, breaking it down into specific, separate subspaces, like little dedicated compartments within the vector.
Compartments. For what?
So there's a part for the main content, what the token is. Then, crucially, there are separate buffer spaces, a first and a second buffer, designed just for holding temporary information. And then there's the usual positional encoding part.
Ah, so it's structured. Content, temporary storage 1, temporary storage 2, position, all distinct parts within the single embedding vector.
Exactly. It's modular, allows the model to perform really specific operations on different pieces of information without them interfering with each other. And you mentioned orthonormality.
Yeah, the paper mentions that content embeddings are orthonormal. What does that mean in practice?
Think of it like this. The signals for different concepts or tokens are kept perfectly separate, like they're at right angles to each other in the model's internal space. U equals IV. It means there's no crosstalk, no bleeding between different ideas. Super clean signal processing, which is vital for tracking multiple things accurately.
Makes sense. Okay, structured embeddings. What else? You mentioned an attention chooser.
Yes, another critical piece. This is a specially designed attention mechanism. You know how attention normally lets the model weigh the importance of different parts of the input?
Right, focusing on relevant words.
Well, the attention chooser is like a precision spotlight. It allows the model, under specific conditions, to focus its attention almost entirely on one specific previous position in the sequence.
How does it do that? How does it know where to look so precisely?
It's a very elegant bit of mathematical engineering. They cleverly construct the query and key matrices, the things that determine attention scores, to exploit the properties of sinusoidal positional encodings.
Ah, the positional math.
Exactly. There's a property where positional vectors can be rotated,
Yeah.
plus OP, and they use this so that the query from the current position lines up perfectly with the key from a specific relative past position, but only if a special trigger token is present. Otherwise, attention just defaults somewhere else, like a designated sync token.
Clever, using the math of positions to create targeted lookups.
Very clever. And they formally prove this works under some mild, reasonable assumptions. Lemma 1 gives the intuition, Lemma 3 makes it rigorous.
Okay, so we have structured embeddings, precise attention. What about the MLP? The feed-forward part, is that just standard?
Not quite standard here. The multilayer perceptron, MLP, acts more like a sophisticated signal filter in this setup.
A filter. How so?
Its main job, after the attention layer has mixed information together to form that superposition thought, is to clean it up. It gets rid of the noise tokens or concepts that have only tiny, almost negligible weights in the superposition.
So it prunes the weak signals.
Exactly. And it also normalizes the weights of the remaining significant tokens. It ensures the continuous thought stays clear and focused on the genuinely reachable nodes.
How does it technically do the filtering?
It's a neat three-step process. First, a matrix W1 rotates the vector into a different basis. Then, a simple nonlinear function, basically a threshold, zeroes out any components below a certain small value.
So it just cuts off anything too small.
Right. Then, another matrix W2, which is just the transpose of the first one, W11, rotates the cleaned up signal back to the original basis. It's designed to preserve the structure while removing the noise.
Okay, that makes sense. Embeddings, attention, filtering. Now, how do these pieces come together in the actual two-layer transformer they built?
It's surprisingly simple in structure, but powerful because of those components. It generates the continuous thought step by step, autoregressively. Layer 1 is the information copier.
The copier, what's a copying?
It uses several attention heads, 5 in their setup, and each one is an attention chooser. Their job is to strategically grab specific pieces of information from the input and copy them into those buffer spaces we talked about in the output tokens embedding.
So if the input is an edge token, say representing an arrow from node S to node T,
then one attention head in layer 1 might use the attention chooser mechanism to find the embedding for S and copy its content part into buffer 1 of the edge token's output embedding. Another head copies T's content into buffer 2.
Got it. So layer 1 basically preps the data, loading up the buffers with the right source and target info for each edge, or handling other special tokens.
Precisely. It organizes everything neatly. Then comes layer 2, the Graph Explorer.
Okay, what does the Explorer do?
This layer has just a single attention head, but it's the crucial one for actually moving through the graph. It looks at the current continuous thought, etc., which, remember, is a superposition of all nodes reachable in C steps.
By the combined state.
It then attends to the edge tokens processed by layer 1. If an edge token source node, which layer 1 put in buffer 1, is part of the current thought, etc., then layer 2 takes the edge's target node from buffer 2 and adds it to the next continuous thought, etc. plus 1.
So it checks, is the start of this edge already in my reachable set? If yes, okay, add the end of the edge to the set for the next step.
Exactly. It performs one step of a graph traversal across potentially many edges simultaneously because it's operating on that superposition. It updates the state to include newly reachable nodes.
So TO starts as just the root node. Then T1 is a superposition of nodes reachable in one step, T2 in two steps, and so on. Each TO EVA vector is the evolving thought about reachability.
That's the core mechanism. It iteratively builds this richer and richer representation of reachability. And then, after enough steps, maybe D steps,
For graph diameter.
an answer token A comes along, and the model looks at the final continuous thought TD, sees which of the candidate destination nodes has the highest weight or similarity within that final superposition, and makes its prediction.
That's really elegant.
Yeah.
But does it actually work in practice? You mentioned the theory is strong, but what about the empirical results?
This is where it gets really convincing, especially from an academic view. The proof is in the pudding, right? They tested it, and the two-layer transformer using this continuous CoT got near perfect accuracy, like close to 100%, on some tough graph reachability tasks.
Like the Prosquier dataset.
Yeah, tasks needing 3 or 4 reasoning steps. And here's the kicker. They compared it to a much bigger model, a 12-layer transformer using the standard discrete CoT.
Yeah.
The big model only got around 83% accuracy. The small 2-layer continuous model absolutely smoked it. Much better performance with way fewer parameters. That really highlights the efficiency innovation.
Wow. Okay, so the performance backs it up. Did they, look inside the model during reasoning? Can you see the superposition happening?
They did. They have some great visualizations. For layer 1, the attention maps clearly show the heads doing that copying job. You see attention focusing precisely to grab the source node info, put it here, grab the target node info, put it there, just like designed.
Confirmation of the mechanism.
Exactly. And layer 2's attention is even more revealing. It doesn't just look at any edge. It strongly focuses on edges where the source node is actually reachable.
The relevant edges.
Right. But more than that, it shows a bias. It pays more attention to edges leading to frontier nodes, the ones exactly at the current step count, and especially to optimal edges that lie on the shortest path. It's not just expanding, it's expanding intelligently.
That's subtle. And what about the continuous thought vector itself, etc.?
They measured its similarity using inner products to the embeddings of all the different nodes in the graph. And just as you'd hope, nodes that are reachable have high positive similarity scores with the thought vector. Nodes that aren't reachable, near 0 or even negative scores.
So the vector genuinely represents the set of reachable nodes.
Yes, but again, with nuance. The nodes on the frontier and the optimal path nodes, they tend to have even higher similarity scores. The superposition isn't just flat, it actively highlights the leading edge of the search and the most promising paths.
Which circles back to that emergence point.
It really does, because remember, they often train these models only on finding the single optimal path. They didn't explicitly reward exploring broadly.
Right.
Yet the internal continuous thought vector still represents this broader BFS-like exploration. It assigns weight to non-optimal nodes on the frontier. That behavior just emerged. It learned this highly effective parallel exploration strategy implicitly.
That is genuinely fascinating, the power of this continuous latent space reasoning.
It really suggests there's a lot going on under the hood that we're only starting to understand.
Okay, so let's recap this deep dive for everyone. The core takeaway seems to be this idea of reasoning by superposition and the chain of continuous thought. It's both a theoretical framework and, empirically, a very effective way for transformers to handle complex multi-step reasoning.
Yeah, by representing knowledge not as discrete text steps, but as this rich, parallel superposition state evolving over time, it's definitely a leap in understanding how these models might be performing reasoning internally, more efficient and potentially more powerful.
It really challenges the old view of AI thinking sequentially, doesn't it?
It absolutely does.
So that leaves us with a final thought for you, our listener, to chew on. If models can implicitly learn sophisticated parallel search strategies, like this BFS and superposition, just from simple training objectives, well, what other advanced reasoning capabilities might be bubbling up, emerging inside these continuous hidden states?
Things we haven't even thought to look for or explicitly train for yet.
Exactly. What does this mean for the future? For AI solving really complex problems in science or logic or planning, how much untapped potential is waiting in these emergent abilities? Something to think about. We'll leave it there for this deep dive.